In the notes for section 2 of chapter 2, we speak about the first and the second derivatives because we're getting ready to talk about first and second derivative tests. But let's just define the first derivative rule first. So if the first derivative is greater than 0, then the function is increasing where it is greater than 0. So, for example, if I give you a curve and I say that here is my A, right here where I draw a tangent line to it, I can see that the slope there at A is positive and therefore the function is increasing. So giving myself a positive first derivative when I evaluate the derivative at A gives me a positive, an increasing function. Likewise, if I want to talk about a function that is decreasing at A, so if my function is decreasing at A, the slope of that function will be negative. So an increasing function gives me a positive slope, a decreasing function gives me a negative slope. We're going to use some of these characteristics to sketch graphs, and we're going to do that on the next slide. Okay, on this page, I want you to practice sketching a graph. I'm not going to give you the function, I'm just going to tell you some things about the function. So when we look at what we know about the function, the first thing we know is that f of negative 1 is 0. This is telling me that the point negative 1 comma 0 is on my function. So the point negative 1 comma 0 has to be on the function. This next line says f prime of x is less than 0, so the slope is negative for x's that are less than negative 1. So I know the slope is negative in this area. My next little piece of information tells me that the slope at negative 1 will be 0. Okay, so the slope at negative 1 will be 0. So I could have a max, a min, or what we're going to call a shelf, which we'll get to in 2.3. Now the last little piece of information tells me that the slope is going to be greater than 0, so the slope is positive when x is greater than negative 1. So I have to put all these four pieces together to get a possible sketch. So the first thing I'd like you to do is let's get ourselves a grid. So here's my grid, and if I know I have to have the point negative 1 comma 0, so here's negative 1 comma 0, I know that that point has to be on my function. What else do I know? Well, I know that the slope has to be negative, so here the slope is negative to the left and positive to the right. So that means that the slope will be 0 right here, and I have this scenario. So this sketch follows the properties of the function that I've identified above. So we're going to do this again in just a few more minutes. Okay, on this page they start speaking about the second derivative rule. And the second derivative rule states if f prime of prime of a is greater than 0, then the function is concave up where x equals a. Similarly, if f prime prime of a is less than 0, then the function is concave down where x equals a. So we talked about concavity and what that means in 2.1. So I have a little graphic here that's going to help you. So if if your second derivative is positive, then you're concave up. That's your first picture here. So remember, These are second derivatives that we're speaking about, not first derivatives. So if the second derivative is positive, you are concave up. If your second derivative is negative, you're concave down. Okay, so that should help you remember the concavity rule. So let's sketch a function that is concave up because it's greater than 0. So we're going to do this one, right? So sketch a function that's concave up at A. So here's my function. Where is it concave up? Well, how about right here at A? It's concave up there. So now where is this function concave down? It's concave down where my second derivative is negative. I'm going to use this face, and I can draw something similar to what I just did, and I can say that right here at A, my function is concave down. All right, be able to understand that and be able to apply it when we speak about concavity. Okay, this is a very helpful diagram that I took directly from your textbook. So they talk about the conditions on the derivatives, and they speaking about first derivative and second derivative, and they're evaluating both derivatives where x equals a. So if your first derivative is positive, your function is increasing, and your slope, so I think I'll make a little slope category right here. Your slope is going to be positive also. If your second derivative is positive, then you know you're concave up, and why is that? Because I have my little positive happy face. All right, so here is an example of what that looks like. So that's your both derivatives are positive. What if the first derivative is positive? So my slope is positive, my function's increasing, but my second derivative is negative. My second derivative is negative, I've got to be concave down, and that's what that looks like. Let's flip that. Let's reverse it. What if my first derivative is negative? So that means my slope has to be negative, but my second derivative is positive, so my concavity is concave up. That's an example of that scenario. And the last one is both derivatives are negative at A. So if they're both negative, my slope is negative, and my concavity is concave down, and that's what that looks like. So go through that, make sure that you could recreate this kind of table if asked to. Okay, on this last page of the notes, or second to last page, it says sketch the graph of a function that has the properties described. So we're going to go through each of the properties, and we're going to write down what does this tell you. Now, you don't have to always do this when you're going to give me a sketch, but this is a way to understand the process. So, for example, the first property is that f of x is defined only for x is greater than or equal to 0. So what does this tell us? Well, it tells me that my function is only defined in either the first or the fourth quadrants or both. Those are the only quadrants where my x is greater than or equal to 0. It can also be on, at the point 0, 0. Okay, the next thing, so that's the first property. Second property, 0, 0, and 5, 6 are on the graph. So these are 2 points, and that's the first thing that we're going to do is graph these 2 points. All right, because no matter what happens to our function, those 2 points have got to be on it. Okay, then our third property, f prime of x is greater than 0 for x is greater than or equal to 0. So that's everywhere. So our slope is always positive. Okay, so that means my function is always increasing. Okay, the second derivative, f prime prime of x, is less than 0 for x less than 5. So I am concave down where x is less than 5. My function, my second derivative of my function is 0 at x is 5. So I have an inflection point there. So inflection point, I know it's going to be at 5. I'm not sure of the y value. Okay, then my inflection point, after my inflection point, my second derivative is greater than 0. So that means I'm concave up where x is greater than 5. Okay, so this is what I want you to notice. You now have been shown that you can find your inflection point by taking the second derivative of your function and setting it equal to 0. So now we're ready for the sketch. So what sketch will have all these features? So I know it has to be in the first or the fourth quadrant. Most importantly, right now, I know the point 0, 0, so that's 0, 0, and then 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6. So this point right here has to be on my curve. Okay, so right there has to be on it. Okay, so what about my slope? My slope is always positive. Okay, my function's always increasing. So I'm going to think about this because I have to do a concavity also. So I know that the point 5 comma 6, so now that's the point 5 comma 6 because I recognize that. So at that point I have an inflection point. That means the concavity is changing. So what do I know? I know that I am concave down up to that point and then concave up after that point. So my blue function satisfies all of these requirements. So look what happens right here. It looks to me at my inflection point that is also a shelf because my slope is always positive. So I don't have a situation where I have a max or a min because my slope is not changing. So this was a situation where we graphed a shelf and we learned this little feature that if the second derivative equals 0, that is our inflection x value, and then we can get the point by plugging it in the original function if we have it. In this situation we got the point because they gave it to us. Alright, the next slide, which is the last slide for these notes, is going to help us understand how we can look at all three functions, the original function, the first derivative, and the second derivative on one graph and make some connections between the three. Okay, so I'm not going to write down below about each of the functions. I'm going to talk about them and you should write notes on them. So maybe I will write something on the side. So let's start over here. I think what I'll do is I'll talk about f prime of x over here. So it's where it's down at the bottom for you, but I'm going to do it off to the side. Okay, so I see the blue curve. Oh, sorry. Let me refrain from doing that. That's just f of x. I see the blue curve is just my f of x. So that's my function. Okay, now interesting things. That function is a cubic. I know that because my first derivative is a parabola and my second derivative is a straight line. So that's the pattern I'm seeing here. Let's look at our original function, and I'm going to put a little dot at the max and a little dot at the min. So I would say that I have a maximum value, So it's going to be a relative max because this is going to go forever and that's going to go up forever down. So it looks to me like my relative max is at the point 2 comma 9. Okay, and my relative min is at the point 10 comma 1. All right, so that's one thing I'm seeing. Let's talk about slope. My slope is positive to the left. My slope is negative to the right of that relative max. My slope is negative to the left and positive to the right of my relative min. My function is concave down, all in here, and concave up, all in here. Now, where is the inflection point? Well, I know that my second derivative is the one I want to look at, where that's 0, so I'm going to see that it's 0 right here. I'm going to come up, and that's my inflection point. So my inflection point is at the x value 6, and the y would be 5. So at 6, 5, I have an inflection point. So in terms of analyzing f of x, I can say max 2, 9. I can say minimum at 10 comma 1, inflection point 6 comma 5. So my function is increasing from negative infinity all the way to 2, not inclusive. It increases again from 10 to infinity, and my function is decreasing from 2 to 10. In terms of concavity, my function is concave down from negative infinity all the way to 6, not inclusive, and concave up from 6 to infinity. Okay? So I can say those things about my original function. I'm now going to talk about what I could say, how I can make connections with my first derivative. So let me change my color to match the first derivative. And what do I see here? All right, I know that my slope is positive here on my function. So I can read my slope right off of my first derivative. So my slope, where x is 1, is about, about 0.5, I would say. Okay, so you can read your slope directly. So here, I can read positive values for my slope. Then here, I'm going to read negative values for my slope because it's below the x-axis. And then here, I'm going to read positive values for my slope. Look at my inflection point. My inflection point is a minimum, on my parabola, which is my first derivative. So this is f prime of x. Okay, what about the roots of my first derivative? Here's a root. That root tells me where my tangent line is 0. Here's another root. That tells me where this tangent line is 0. So the roots of my first derivative are the max and mins of my original function. Okay, so that's kind of good to know. Let's look now at my second derivative. So my second derivative is the green one. What do I see? Well, the second derivative tells me about concavity. So I see that my second derivative is negative all here, because I'm reading off the y-axis, and then it's positive all here. So what does that tell me? In this area right here, it's negative. I'm concave down, which is what I'm seeing looking at my function. The turning point of the concavity is at the inflection point, where my second derivative equals 0, and then all in here, my second derivative is above the x-axis, so it's positive, which makes it concave up. So I measure concavity with the second derivative, I measure slope with the first derivative, and I measure the whole function with the original function. So there's a lot of connections between these two curves. You can tell a lot about your original function by analyzing your first and second derivative. So go back, make sure that makes sense to you.